Today we'll discuss instruction fetch for wide issue superscalar processors. So the goal is try to fetch as many instructions as possible per cycle. So this is called fetch bandwidth. Instruction fetched, number of instructions fetched per cycle. You are trying to increase number of instructions that are fetched from memory. Because the job of this front end is providing instruction stream to the back end. Okay, we are trying to provide as many instructions as possible, because if you want to implement wide issue superscalar, if your front end cannot supply enough instructions, that the back end will store, because they are most of the time they are waiting for front end to wait for instruction. So the job of front end is trying to provide as many instructions as possible, so that back end can consume as much as possible. Okay. And due to several reasons, it's not easy to provide many instructions per cycle. So this instruction fetch bandwidth is limited by, we have basic block. At the end of basic block, we have branch instruction, which can go to another cache line. So if you can fetch only one block, one cache block at a time, the maximum you can get is maybe from the starting point of this instruction until the taken branch that are in the same cache line. So it can be one cache block, or it can be more than one cache block, because the conditional branch might not be taken. If you are lucky, then you can provide more. But basically, you are limited by cache block size and control branches. And even if you supply, you think you supply instructions to the back end, you are using branch prediction, speculation. You are assuming this path will be taken in the future and supplying instruction stream from that control flow path. But branch prediction hit rate, because of it's not perfect. Whenever you mispredict, the instruction you supplied is no longer useful. It has to be flushed from the pipeline. So there is a cost of redirecting, fetching from the correct control flow path, and you need accurate branch prediction. Otherwise, without accurate branch prediction, this high instruction fetch bandwidth design is not easy. And the other issue is branch throughput, which means maybe 3 or 4 issue, you can assume only one branch instruction every cycle. But more than 3 or 4 issue, for example, for Itanium 6 issue superscalar, you may encounter more than one branch instruction every cycle, if you want to supply more than 4 or 5 instructions every cycle. Okay, that requires multiple branch prediction using a single program counter or single fetch address. You need to predict multiple branches. That's not easy. And anyway, even if you have all of these, whenever you have a taken branch, you go to another cache block. So if you fetch only one cache block at a time, then your maximum fetch bandwidth is limited by block size and limited by taken branch. And if you want to support more, you need to fetch multiple cache blocks every cycle from the cache because of this taken branch. And that also requires you have to fetch multiple non-contiguous base blocks, and you have to align cut and paste and align and send them to the backend. And this will increase the pressure for instruction cache, because you encounter more instruction cache message and so on per cycle, in terms of per cycle. So you need to provide good instruction hit rate. So you need to have larger instruction cache or maybe prefetching mechanism that can supply instruction ahead. So front-end design for wide issue superscalar is not easy. And we are looking at two different solutions. One is called branch address cache, proposed by Seiyue, who proposed two-level adaptive training scheme. So after his work on this branch prediction, he was thinking of this instruction fetch bandwidth issue for wide issue superscalar, because at the time, trying to implement more wider and wider issue superscalar was the trend for processor design. And because of all these issues, it was not easy to supply high instruction fetch bandwidth. And he come up with a solution called branch address cache, which is a kind of straightforward or natural extension of existing branch target buffer or target address cache. Because we have studied branch target buffer that contains, for each instruction we have target address and 2-bit bimodal predictors, 2-bit counters. But 2-bit counter you can only supply 93%, about 93% accuracy. If you want to increase your condition prediction accuracy, you need to implement more aggressive scheme, which we have studied, two-level adaptive training scheme. There can be local predictors, or there are global predictors. You can have G-share, you can combine global predictor with bimodal predictor by combining program counter with global history register. Okay, so there are some global schemes and local schemes, and then you can also implement tournament predictors, which means you can combine different two predictors and you can select some optimized predictor for each branch. Okay, so we have studied, you can come up with about 98, 97, 99% accuracy. Okay, so branch target buffer, the original design with this two-level adaptive training scheme. Let's say the common solution for high-performance processor is you use tournament predictor, G-share with maybe local predictor, or G-share plus bimodal predictor, and so on. Okay? Then you don't need bimodal predictor in the branch target buffer. So branch target buffer needs to store only the target address, and it's called target address cache, because you only store the target. Okay? So target address cache has only one target address for each branch, and you have tournament predictors that provide condition prediction, and this provides target prediction, and it also provides whether this is a branch or not by looking at the tag in the target address cache. The branch address cache, if you want to supply multiple non-contiguous page block every cycle, somehow you need multi-way branch prediction. Okay? Multiple branch prediction. Single branch prediction, you cannot do that. You need multi-way branch predictors, and you need to supply multiple target address every cycle, because you want to fetch multiple page block, multiple non-contiguous page block. Okay, let's look at this organization. So, for superscalar processors, you provide fetch address. Using this fetch address, you somehow predict this conditional branch, which might be at the end of this page block. Okay? Okay, so the fetch address may not correspond to the branch instruction address exactly, because you are fetching multiple instructions. Okay? So using the fetch address, you are trying to predict the first conditional branch, whether that will be taken or not taken. Based on this prediction, there are two paths. It can be taken or not taken, and you have two target address. For taken, this is the target address. This was the normal target address for target address cache or branch target buffer. Okay? For not taken, maybe next sequential fetch block, which might not be program counter plus 4, since you are fetching multiple instructions every cycle. Maybe your PC plus 4 times 4 or something like that if you fetch 4 instructions at a time. Okay? And then this primary basic block, you need to predict another branch. This is called secondary branch. Okay? Using this as an address. Okay? So there are two conditional branches. There are 4 possible combinations. This one will be taken, not taken, taken, not taken. So you need to provide 1, 2, 3, 4, 5, 6 target address if you want to do two-way branch prediction, which means two branch prediction every cycle. Okay? So if you assume the multi-way branch prediction assumes taken, then you provide 2 target address and you are fetching this 2 basic block. And using this target address, you start from the beginning again in the next cycle, and 2 at a time. Okay? This is for 2-way branch prediction. If you want to supply 3-way branch prediction, another level, and there should be 8 taken. It's like the truth table. Okay? So every level, you have first level, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. You need to provide many target address. Okay? Because there are many combinations. Okay? So target address cache becomes bigger and bigger as you increase the branch prediction throughput. Okay? Okay, so you think maybe it might not be efficient because there are too many target addresses, but we can do that. Okay? And the other issue is, can you implement multi-way branch prediction? That's another issue. Okay, we can supply multiple target address every cycle, even though the target address cache becomes bigger and bigger. That might be okay. Okay, we can do that. How can we implement multi-way branch prediction? So he was thinking of, can he modify local predictor so that it can work for multi-way branch prediction? And he also worked on global predictor, how we can modify. And local predictor, it was not easy. After you predict, you have to go back and predict again. And it will slow down the branch prediction. Branch predictor table access, because you have to sequentially access branch prediction tables. But for global predictors, there is some way. You figure out that you have this global history register that contains the last k branches encountered. And this was the most recent one. This is the oldest one. Normally, using this k-bit history, you access your pattern history table, and using the MSB of this bimodal predictor, you can predict either it will be taken or not taken. Okay? But for the next, for 2A branch prediction, this is not enough. You need k-1 and another result of branch history. But that's not known, right, at this time. But the issue is at least k-1 history is available. And if your global predictor is quite accurate, global predictor can support up to about 96% accuracy, you can use this prediction, current prediction as a history. Okay, that's the idea. So you can predict first condition prediction, right? Using global predictor. The next one, you can use k-1 history plus this one. Okay? For the next level of branch predictor. And then that means you use k-1, it will select 2. Okay? And then using this last, the current prediction, you can select 1. Then it will supply secondary branch prediction. Okay? You don't follow? So let's say you have 4-bit history, 1, 1, 1, 0. Okay? So normally you have this 2-bit counter array, and this is 1, 1, 1, 0. And this might be 1, right? And using this as an index, you access this entry and you predict the next one will be taken. Okay, that's the global predictor. Okay, we want to figure out the following, the next one, branch prediction for the next branch. So it will be, after this cycle, taken, they predict taken, but after this branch execution, it might be taken or not taken. We don't know. So basically, we cannot predict. We don't know. But next cycle, it will be 1, 1, 0. And if your prediction is correct, it's likely that this will be your history. Okay? Clear? This will be your history. So, depending on this value, using this as an index, if you go here, there will be 1, 1, 0, 0 or 1, 1, 0, 1. 2 entry. And there are MSBs here. And using this MSB, you can predict, but you don't know which one. But you can select using your prediction, assuming your prediction is correct. Okay? So if this is 1, then basically you will select this one. So MSB might be 1 or 0, I don't know, right? Well, if this is 0, then you will select MSB of this entry. Okay? And assuming your prediction is correct, that will provide you the secondary branch prediction. Okay? For 3-way branch prediction, you need another level of box. And you can select one out of 4 using this 2-bit predictions and so on. So, because this is not accurate, actual history, for secondary branch prediction, the accuracy will be reduced a little bit. So ternary prediction, it will be reduced further. But it might be reasonably good, okay? That's the motivation for multi-way branch prediction. Oh, so he thinks it's possible, okay? So this might be the idea. So he suggests this one, multi-way branch predictor using global history register. And then he designed this target address cache and modify so they can supply multiple target address. And he called this structure as a branch address cache instead of target address cache. Okay? So for 2-way branch prediction, he supplied 6 target address. Taken address, not taken address. Taken, 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 not taken. This should be NT and NN. So this is typo. Okay? So for target address, for each branch there are some valid bit and what kind of branch, whether it's a conditional branch or unconditional branch or something like that. There are some boundary conditions, okay, to implement. But anyhow, he can supply. Okay? So basically for three-way branch prediction, branch address cache needs to provide 2 plus 4 plus 8, 14 target address. So the issue is target address cache becomes quite huge to implement multi-way branch prediction with multiple target address support. But that's possible. Okay? So it's more like a straightforward extension of existing target address cache and existing branch prediction structure. So he shows that it's possible to build, but it might not be efficient because the target address cache is too big compared to your benefit, which is multi-way branch prediction. Let's look at his simulation, how much he can get. He can increase the fetch bandwidth using this structure. And another issue he needs to come up with is, okay, so he can provide multiple target address. The other issue is you need to fetch multiple cache blocks from instruction cache because you are providing multiple target address. Okay? How to implement instruction cache that can support, you need to fetch multiple cache block every cycle. Okay? So there are, originally, the common solution is multi-ported cache, which means you provide 2 different address and it can fetch 2 different cache blocks every cycle. Okay? 꺼졌나? 이게 꺼졌네? 배터리가 나왔네. So multi-ported cache means for single port cache, for SRAM, cache is SRAM, okay? So you need basically 6 transistors, because you need, the SRAM cell required 2 inverters, which is a NOT gate. So you need, for each inverter, you have 2 transistors for CMOS, okay? So 4 transistors, at the end you have to select the data and read, so you have 2 pass transistors attached to this inverter, so that requires 6 transistors. To implement 2-port, dual-ported SRAM cell, you need to add 2 pass transistors for every port. Okay, so 8 transistors, 10 transistors, and so. But if you want to have the same speed, then the transistor becomes bigger and bigger, and the size becomes bigger and bigger. So usually they call multi-ported cache design is quite expensive. Okay, but that's the common way of implementing multiple cache blocks per cycle for instruction cache access. And he suggests that's too expensive. So instead of that, you can use interleaved cache organization, which means so you divide the cache into 4 different banks. And for this cache, for first bank, the address is mode 0, mode 1, mode 2, mode 3. Address NZ divided by 4 becomes 0, 1, and 2, and 3. So you distribute cache block in this way. Okay? And so on. And if your address, fetch address, goes to 4 different banks, you can support at the maximum speed 4 cache block every cycle because you can access each bank independently. But somehow your address goes to the same bank. In the worst case, if 4 fetch address goes to the first bank, then you only can supply a single access. every cycle. This is called interleaved cache organization. But these bank conflicts are not common, so in general, you can supply maybe 3 or 4 or 2, more than 2, right? Cache blocks every cycle. That's without multi-ported cache, because each cache block, if you look at the cell, they are supporting one access every cycle. You don't have to have dual-ported SRAM cell or triple-ported SRAM cell. Okay? So in general, to have higher fetch bandwidth, there are 2 options. One is multi-ported cache, the other is interleaved cache organization. Multi-ported cache means you have 2 inverters, and these are 2, and you have so here, this is the bit line, and this is the selection line. So address goes here, you select this one, and you can read the data. So one provides Q, normal, and the other provides Q bar. Okay, this is the SRAM cell. If you want to support dual-ported SRAM cell, you need another another 2-pass transistor for every port, for each additional port, and you can provide 2 different addresses. Okay, but that increase number of transistors and the size, which will increase the size of instruction cache. So this is just he's suggesting. Okay, so nothing new actually, and since more instructions are fetched every cycle, there are fewer cycles between instruction cache miss. So this might be the bottleneck. So you need to have increase cache size to increase cache hit rate, right? Or you need to increase associativity, or you need to supply prefetching, okay, to sustain this high instruction fetch bandwidth. So this is all straightforward extension using existing solutions. Okay? So he did some simulation and he compared, this is for integer benchmark, this is for floating point benchmark, and this is integer average, this is floating point average. And the first one is single branch prediction per cycle, and the other 2 is branch address cache with 2-way branch prediction, 3-way branch prediction. As you increase this prediction branch prediction throughput, you increase this fetch bandwidth. Okay, so this is supplying 2 plus 4, and this is supplying 2 plus 4 plus 8 instruction using the branch address cache. Okay, so for integer, this is IPCF, which is instruction fetched per cycle. It's not actual performance, which is IPC, instruction per cycle completed. This is just fetch bandwidth. So originally, for integer application, it can supply only maybe about 3 instructions every cycle with single branch prediction. But with 3-way branch prediction, you can increase this almost up to 5 for integer application. For floating point, on average, because floating point there are less number of branches, so you can supply high number of instructions per cycle. So with single branch prediction, maybe about more than 6 or close to 7. By using 3-way branch prediction, you can increase more than 8. Okay? Okay, this is the total average. Okay, so this is somewhat traditional, typical academic paper. We can do that by extending the existing design, but it's usually too expensive, not efficient, and it's not adopted by commercial processors. Okay, so many people are working on this idea, and this is one solution by Seiyue. And the issue is to fetch multiple cache block every cycle. If you implement multi-ported cache, it's too expensive, but if you use interleaved cache organization, there are bank conflicts which will reduce your fetch bandwidth. And even if you have branch address cache with multiple branch prediction, you need this complex shift and alignment logic, because you fetch multiple cache block, you extract this basic block from each cache block, and you have to align them every cycle, which will take time, which will decrease your cache access time, increase your cache access time. And the biggest problem is the number of target address stored in branch address cache increase substantially as you increase this branch prediction throughput. 2, 4, 8, 16, and so on. It's exponential. Okay? So, it was proposed, but it's not actual practical scheme. Okay? And other people also suggest similar schemes. Okay? So this paper, I remember this was proposed in maybe late 90s, 89 or 90 or something like that. And there are other papers like collapsing buffer, which we'll study in this one. This is branch address cache by Seiyue, and this is collapsing buffer proposed by Thomas Kuhn at North Carolina State. Okay, another person about the same. About the same time, but around 1995, about 5 or 6 years later, this Rothenberg and Jim Smith, the famous person at Wisconsin, come up with a trace cache. Trace cache is quite simple. Okay, so usually good idea means it's quite simple and intuitive. If your idea is too complex, it means something wrong. Okay? Changhyun, so if your idea become too complex, then it's not an idea anymore. It's some mix of several different ideas, and it doesn't work usually. The trace cache, the idea is, okay, traditionally, instruction cache stores static instruction stream in each cache block. Okay, so you have virtual address space, memory space. So you divide memory into a cache block size, and each cache block goes to this instruction cache. Okay, so this virtual address space is actually program space. Okay. 여기 전에 스택 들고 있는 것 같은데 스택 탑. But the actual dynamic instruction sequence that you are executing at runtime is quite different from static instruction stream. So let's look at this dynamic instruction stream. So basically, traditional instruction cache, you divide this program space, virtual address space, into cache block size, and each cache block goes to here, right? And it can map, depending on this cache organization, it can be a direct mapped, or set associative, or fully associative. In a fully associative, every memory block can go to any of these cache blocks. In direct mapped, you divide the address space into cache size, and the first block goes to the first one, the second block goes to the second one. Okay? So there is only one cache block you can go to. That's called direct mapped cache. Set associative cache is in between. Anyhow, each cache block is coming from the program space, and these store the program statically, a static instruction stream. So if you look at these cache block, it might contain multiple page block, right? Actual dynamic instruction stream might be after you execute this page block, this is not taken. So you go here, this is taken. You may go here, you go, and this is taken, you go here, and not taken, and this goes back to here or something like that. Okay? So dynamic instruction stream becomes actually 1, 2, 3, 4, 5, and maybe another 6 and so on. That is the dynamic instruction stream. The instructions you are actually executing at runtime. That's different from the program stored in memory. Okay? And his idea is, let's store this dynamic instruction stream. And it's called trace. You know, it's cache. Okay? So each trace cache, each cache block is a trace. So maybe in a trace cache they store and then and so on. So you have 4 basic block trace in your trace cache line. Okay? And because usually if you look at the program, they are going to the same path again and again because usually the branch are biased into one direction. So even the dynamic instruction trace has a locality. You are executing the same path again and again. And once you execute this path, you store this trace. Next time you execute the same control flow path, you can find the instruction from the trace cache. Okay? And the idea is because you already stored your trace in this trace cache, you don't have to fetch multiple cache blocks. It's in the same cache line. Okay? And you need no alignment logic because it's all aligned already. As long as your prediction, so you need also multiple branch prediction. If this should be a trace cache hit, then starting at this target address, this might be not taken, this might be taken, this might be taken. Okay? So same target address. If the predictor says NTT, then you can use this trace. Okay? That is the trace cache. This is quite simple. Okay, so, this might be better than branch address cache. Okay? Intuitively, he think. Let's try to do some experimentation. Whether this really works or not. Okay? So, he elaborated his design. The trace, he defined a sequence of dynamic instruction stream. It contains at most n instruction because it's limited by trace cache block size, cache line size. Okay? Each cache line might contain only 16 instructions or something like that. That's the maximum. And it might contain n basic blocks, which depends on the branch prediction throughput. Okay? Because you can support up to 3 branch prediction, then maybe you can have up to 3 basic blocks. Okay? The last branch, so maybe NT, and the last one, you should use that for the prediction for the next cycle. Okay? So this trace is specified by the starting address, which is the tag, and n-1 branch outcome. Okay? If the trace cache line has the same starting address and the predicted branch outcomes, so when you store this trace, you have to store the tag and this one also. And if your predictor says the same target address and entity, then you hit the trace. Okay? Otherwise, it's a cache miss, and you can fetch from the instruction cache. So you have 2 time level cache. One is trace cache, the other is instruction cache. So if you hit trace cache can supply more instruction, so you fetch from the trace cache, otherwise you fetch from the instruction cache, and this is the design. Okay? Okay, so for this example, it's assuming three-way branch prediction. So you provide fetch address, and here this is normal instruction fetch logic, front end. So you have return address stack, you have branch target buffer, and you have branch predictors that provide condition prediction. Okay? And you have instruction cache. And this is an example of trace. Okay? And the predictor supply m branch prediction. So in this case, 3 branch prediction every cycle. Okay? So fetch address is going into branch target buffer and instruction key normal front end, and also into the trace cache. Okay? And from this 3-way branch prediction, 2 branch prediction results are going into here. And this one says these trace starts at this address tag, and this first and second branch will be taken and taken. So TT, A, TT, taken, will specify this trace. Okay? So n-1 prediction results with this fetch address, if you match tag and this branch flag, which is the result of this first and second branch, then you have a trace cache hit. Okay? Let's see. And the third branch is used for next fetch address. If third one is taken, you provide this target address. Third one is not taken, you provide this false address. Okay? So instead of branch address cache, you only need to provide 2 target address. One is target, the other is false row. Taken, not taken, for the last branch. And these are the boundary condition. You need this kind of information. It's called branch mask. This is how many branch instructions are in this cache block. Sometimes there might be only 1, or 2, or 3, or 4. Okay? It said it has 3 branch instructions in this cache block, and this another flag is called, is one of branch mask. This is whether your trace ends with the branch or not. That kind of information is needed for boundary checking. Okay? So you might hit here. So instructions can come from your trace cache or can come from the instruction cache. And there is a 2-to-1 MOS. Depending on hit or miss result from the trace cache, you select either the instruction stream from the trace cache or from the instruction cache. And you provide this instruction latch. So normally at the beginning, this will be a miss. And you fetch from one page block at a time from your instruction cache, and you store into the instruction latch. It's kind of buffer between front end and back end. And you supply this instruction stream into the field buffer. Field buffer is a buffer to store cache block in your cache, because you have to build up your trace. You build up your trace in the line field buffer, and after it's complete, then you store into the trace cache. Okay? That's the basic trace cache mechanism. And it's quite reasonable. You don't have to supply lots of target address, only 2 target address. It's quite simple. It's not that difficult to implement. Okay, so he did some simulation, and the good thing about this trace cache is there are many different design options you can experiment. Okay, for this trace cache, you can implement as a set associative cache, or direct mapped cache, or fully associative cache. Okay, that's the normal cache design. Okay? Or you can also have the option of providing path associativity, which means starting at the same target address, right? From starting at address A, would you provide different trace? Starting at the same address, one trace might be same address A, but taken. The other trace might be starting at A, not taken. There are different combinations. You may allow or you may not allow. Normally, if you use tag, only using the tag, then there should be only one cache line starting at the tag, right? You don't allow multiple entries. That means you don't allow path associativity. But if you use, when you access the cache, if you use in addition to this tag, use this branch flag as an index, okay? So it can be A11, A10, A01, A00, entire tag plus branch flag as an index. Then you can allow path associativity, same target address, but you can allow different trace. So that's the another option. You can do that. The other issue is, what about partial matches? It says the trace is tag A and taken, but your result is branch prediction is tag A and taken not taken. So only partial match. Instead of throwing away, you better use the partial trace at least. So there are partial match issues. And as I said, using this index, you can support this path associativity, and multiple field buffer means you are trying to build one trace cache line, right? Until you miss. But there is another miss to the different address, starting a different tag. If you have only one field buffer, you can build only one at a time, so you may have to ignore. But if you design support multiple field buffers, then you can build these multiple trace cache lines at the same time in parallel. And you can. So if you have multiple field buffer, you can improve your trace cache performance. Another issue is called victim trace cache. Victim cache is one of popular design used in processors. Is proposed by Norman Joffé, one of famous computer architect in DEC Western Research Lab. I'm not sure he might be now with HP or not, but he was quite famous person. And direct mapped cache, if you have direct mapped cache, the issue is you have many bank conflict message. Okay? If you are unlucky, even though there are many empty entries, your access pattern goes to, as I said, direct mapped cache means you divide memory into cache size, and the first block goes here, the second cache size, the first block goes here, and so on. Okay? So that you limit the entry you can look up, right? So that you can simplify the logic for the cache design. And if your access is distributed evenly, then you can utilize this cache block efficiently. But if you are unlucky, you might access all this, the first cache block, then that will go to the first cache block, and there will be a conflict miss, even though you have many empty entries. Okay, because it will replace, every time you access a new block, it will replace the previous one. Okay? So to avoid this kind of bank conflict and conflict miss, you can have set associative cache. Okay? That's one option. So you divide this cache into help size bank, and you divide this cache into this bank size, and for each bank, because it's help size, it can either go to here or there, so that you have more freedom. Instead of limiting only one entry, for 2A set associative cache, you can provide two different entries. For 4A, you provide 4 different ways. That's one option. The other option is, okay, let's say direct mapped cache is fine. But the problem is, whenever you have a conflict miss, you have a victim Victim is the block that is replaced. Okay? Usually you throw away these victims, but instead of throwing away, you assume that you have a small, fully associative cache. You put this victim in this victim cache. Okay? Because in direct map cache, these victim blocks are the issues. You have access to the victim block before, but because of conflict, it has been replaced. You cannot no longer access. And it is called cache miss if you access the victim block again. But since you can store into the victim cache, even if you miss, you can find from here, if you have a victim cache. So all the conflict miss, if you supply a small, fully associated cache called victim cache, then you can actually capture most of your conflict message. That is called victim cache, and you can do that to your trace cache. If your trace cache is direct map cache, you can supply a fully associated small victim trace cache that can increase your hit rate for conflict message. Okay, and there are some other small minor issues, and this actually activates a lot of research in computer architecture. After this paper is announced, many people suggest a new variation, new or optimization of this trace cache. So, 1995, after 1995, around year 2000, more than maybe several hundred papers in the trace cache. Always the good paper, it should be simple, the idea should be simple and intuitive. It should suggest a lot of new ideas, lots of variation. The same applies to the two-level adaptive training scheme, right? It's not simple, but it's not that complex, and there are many variations. And people work on that area, and then they improve this branch predictor design substantially after this two-level adaptive training scheme. And same applies to trace cache. After Rothenberg suggests this idea, many people come up with a new optimization, and trace cache becomes more and more optimized, and it's been adopted by commercial processors such as Pentium 4. I'm not sure about i7, but nowadays Intel no longer how do I say? They no longer announce their detailed microarchitecture. So it's not 갑자기 영어 단어가 안 생각나요. But they might use the same trace cache because they start to use trace cache starting from Pentium 4. Okay? If you want to support high instruction fetch performance. So he did some experimentation. Assume unlimited hardware resource constrained by only true data dependence and unlimited register renaming and fully dynamic execution, which means he assumed ideal backend. Backend has as many execution units as possible, maybe 16 integers, 16 floating points, 16 multimedia, and so on. And it's limited by only data dependence, and he can do full register renaming, which means you can eliminate write after read or write after write dependence, and full out-of-order execution. Backend is more like a beast. He can do everything. Okay, aggressive, ideal backend. So backend can consume as much as possible. So by different front end, how much IPC or performance each front end can provide. And he compared. This one is one page block at a time. Sequential 3 is 3 consecutive page block, which means only one cache line. Right? But you provide multi-variable branch prediction up to 3 page block at a time. If they are not taken, then you can supply. This is called sequential 3, and their design trace cache and say edge design branch address cache. This one is similar to this say edge scheme. Same level of performance, same level of complexity. So this is, in this figure, this is performance figure, IPC, instructions completed per cycle. Okay? And these are two benchmarks. One is spec 92, the other is IBS. This is benchmark is to emphasize fetch bandwidth. This is for instruction cache performance. There are another set of benchmarks. And this trace cache for all different applications, it shows the best performance. It's better than branch address cache, even though it's simpler than branch address cache. Okay? And for IBS also. And they show also relative performance. This is improvement of sequential 3 over sequential 1, which means 3 consecutive page block. If you can supply 3 consecutive page block with maybe 3-way branch prediction versus only single branch prediction, single page block. On average, smallest maybe 5% up to 40, more than 40, but on average about 15% performance gain using 3-way branch prediction, even though one cache block at a time. And this is improvement of this high performance fetch architecture compared to sequential 3. They all require multi-way branch prediction, multiple cache blocks every cycle with alignment logic or something like that. And for all these applications, trace cache performs the best, and the lowest performance gain is about 4% to up to 25%. On average, more than 10% or maybe less than 15%. So he suggests as much you can get from multi-way branch prediction, you can get it from the trace cache compared to 3-way branch prediction with consecutive page blocks. Okay? So it was quite simple and intuitive, and it works better than the previous design. Okay? And he did study, depending on the size and the organization, how much efficient this trace cache is. So you have two miss rates. One is called trace miss rate, which is actually for the trace cache, it can be a hit or miss. And the second is how much instructions are not supplied by trace cache. Because trace cache, even if you usually on a hit of trace cache, you supply more instruction stream compared to instruction cache. So even though for this 4 kilobyte direct map cache for this IBS benchmark, trace cache miss rate is about 70%. So only 3 out of 7 you hit trace cache. Okay? So it's quite high miss rate. But if you look at the instructions supplied by trace cache, this means almost half of the instruction stream you can supply from the trace cache, even though miss rate is almost 70%. Okay, you can supply more instruction. Okay, and this IBS benchmark is actually pushing pressure to the front end. If you use spec benchmark using the same architecture, trace cache miss rate is much lower, maybe about 50%, and the instruction miss rate is maybe about 30%, which means with small trace cache, you can supply about 70% of instruction from the trace cache, only 30% from the instruction cache. Okay? So the miss rate, even though miss rate is high, trace cache can provide good instruction stream because trace means you can provide much longer instruction stream compared to instruction cache. And if you increase this cache size to 32 kilobytes with 4-way associative cache, this 70% miss rate for IBS benchmark can be reduced to about 50%, and the instruction miss rate is about 30%. And if you do the same to the spec benchmark, then it will be quite effective because this IBS is stretching or pushing pressure to the front end, but normal benchmark, small trace cache is enough to have a reasonable performance. Okay? That's what they're claiming. So, Itanium actually use some buffer between front end and back end. Okay? So Itanium is 6-ish processor, and if I remember correctly, right after the instruction fetch, there is an instruction latch or buffer. It contains maybe about 12 instructions or something like that. I don't remember exactly, but there is some buffer between front end and back end. What should be the advantage of having this instruction buffer? What is the advantage? Why do they have this buffer? Minji, any idea? 창현, do you have any idea? Any answer? Why do they have buffers? So they usually have this kind of buffer between front end and back end. The reason is you can decouple from front end and back end without buffer. Okay? Sometimes front end is faster, sometimes back end is faster. Without this buffer, sometimes back end might have to be stalled because front end may not supply instruction. Even though back end can consume, it has to wait. Okay? Sometimes front end has to stall because back end is slow, maybe because of dependence or whatever. They cannot consume as many instructions. If the back end is stalled, even if front end can supply instruction, it has to stop. But with buffer, you can store the instruction fetched into this buffer, and you can still work. The front end can still work on. The back end also. Sometimes even the front end cannot go on. They have supplied instruction before and it's in the instruction buffer. So you can still consume instruction from the buffer. So it provides some kind of buffering between front end and back end, and front end and back end can work on independently. So you can decouple. Okay? That's the idea of this instruction buffer between front end and back end. And in Itanium processor, with this buffer, they actually increase the performance of Itanium by about 8% by decoupling front end from the back end. Okay? How can you add path associativity to the normal trace cache line? As we have studied, if you use tag plus branch flag as an index, you can support this path associativity easily, right? Okay, let's have a break and come back.